All right, welcome to topic 6.6. In this topic, we're going to be working on polarity. So, the overall theme with this unit so far is we're looking at how electrons are utilized within a chemical bond. We started the unit by looking at what is an ionic bond versus what is a covalent bond. And so, one of the things I mentioned very briefly at the beginning of this unit was that when it comes to electron sharing, which is what takes place in non-metals, that we can have a difference in the ability of sharing. And what that results in is a characteristic called polarity. Going back to first semester, we talked about periodic trends. And one of the periodic trends we discussed was electronegativity. Electronegativity is an element's ability to attract electrons. If you look at this chart where it shows the scale, again, electronegativity increases as you move up a family, which again is a column, and increases as you go left to right across a period. Notice that fluorine is assigned the most electronegativity, and notice the noble gases are left out. Again, noble gases have a complete octet, and so they have a stable electron configuration. Therefore, they are not trying to gain or lose electrons, so they are not trying to attract. And so fluorine, because of its atomic size and its placement in its configuration, is the most electronegative. And so because they have different electronegativities, that attraction for electrons, their ability to share electrons results in different types of chemical bonds. What polarity does is it shows within the electron cloud how well, or we could say how unwell, electrons are shared amongst two elements. And so the ability for electrons to be shared is all due to that electronegativity. There are three types of bonds that result from this difference in electronegativity, meaning their polarity. We can get covalent bonds of two types, polar and nonpolar. Again, the term covalent indicating a sharing of electrons. And so in the first diagram A, we see that the cloud, that electron cloud is displayed in gray there, it's symmetrical. And so it's showing us that the electrons are being shared equally amongst the two atoms. When you look at B, you see that the dark blue is indicating areas of electron-rich areas, and the red are electron-poor. And so they are sharing the electrons between the chlorine and hydrogen, but because there is a greater difference in their electronegativity, chlorine has more gain on those electrons. It has a greater attractive force for them, and so it kind of creates this lopsided electron cloud. Lastly, the ionic bond is essentially a very extreme polar covalent bond, so extreme that there is no sharing of electrons, but rather a complete transfer of electrons, where the sodium becomes an ion through the loss of the electron, and chlorine becomes an ion through the gain of the electron. So it's completely stripped away. And so they're showing that blue and red, again, indicating areas of electron rich for the blue and electron poor for the red. So a little bit more of a breakdown of those three types of bonds. Like the first one between the two chlorine is what's called a nonpolar covalent. So a lot of times my students will write just nonpolar and they forget that there's also that covalent aspect to it. And so again, when we see covalent, we know covalent bonds are formed between two nonmetals. And so the nonpolar part of that indicates that there's equal sharing. So the types of elements that will create this type of bond are those of similar electronegativity. And so we have to have nonmetals because it's covalent, but typically you see nonpolar in things that are of the same type. So what we call diatomics. Diatomics, again, are the 7 elements that exist in nature on their own, paired or bonded to itself. And so we've drawn a few Lewis structures. So here we see 2 fluorine atoms bonded together. That is one of the 7 diatomics. You're going to learn this acronym here pretty soon when we get into chemical reactions, but the way of remembering those is what I call Hoffenkleiber. So these 7 elements in nature do not exist on their own, but rather bond to themselves. And since, if you think about it, like this example here with the game of tug of war, if you were playing tug of war on yourself, you would have the same pull, meaning the same electronegativity. And so because the electronegativity difference is basically none, or essentially next to none, we get symmetrical sharing of the electron cloud. And so one of the ways we can determine what type of bond is going to result is through the difference in their electronegativity. If we find their difference to be less than or equal to 0.4, we say that this is a non-polar covalent bond. So polar covalent bonds are where we have unequal sharing. And so typically something with a greater electronegativity takes those electrons, and those electrons spend more time in the electron cloud around the element that's more electronegative than that of the lower electronegative. And so here we have fluorine with hydrogen. And so if we were to look at their electronegativity values, we would find fluorine is much more electronegative than hydrogen. And so what happens is a skewed distribution of the electron cloud. Here they're kind of showing chlorine as a villain over the hydrogen here, and trying to show that unequal distribution of the electron cloud. So we can find this combination between nonmetals and metalloids. Typically, they're spaced further apart within that nonmetal region because you need a larger difference in electronegativity. So it's something that's greater than 0.4, but less than 1.7. If the difference in that range, and we'll talk about that difference here more in a moment, that is what's going to help determine if that specific bond is polar, nonpolar, or the last option, ionic. And so ionic, like I said, is a complete transfer. We found that ionic are found between metals and nonmetals. And the reason why an ionic bond forms between metals and nonmetals is because of that electronegativity difference. There's a complete transfer of electrons because their nonmetal tends to have a much higher electronegativity than the metal. And so when your electronegativity difference is greater than 1.7, you would then find that is an ionic bond. So like I said, it's essentially a very, very extreme polar covalent bond that is found specifically with the metals and nonmetals. And again, that electronegativity then determines the bond type. So I'm going to switch the screen here, and what you guys are going to need is our VSEPR table. You probably noticed the VSEPR table had not just the geometry shapes on the one side, but the back side has a periodic table with electronegativity values on it. So parts of the periodic table are missing, and I just completely cut out the inner transition metals or the F block because we, quite frankly, don't really work with those when determining the bond type. And so what we're going to do to start is look at a series of bonds between elements, and we can figure out what type of bond is going to form. So for example here, magnesium and chlorine, you're going to start by finding their electronegativities. And so it really doesn't matter which one you plug in the formula, so to speak, when we find our difference. The big thing is that it should be the absolute value when you're done. Typically, I just substitute in my largest value from my smallest. So knowing that chlorine has an electronegativity of 3.0, and magnesium is over here at 1.2. And so when we go to find our difference, again, you can just take the largest from the smallest. If you don't do that and you get a negative, just make it a positive. So what we get here is 1.8. In the next one we have, if you were looking at the individual bond between a hydrogen and an oxygen, what we're then going to do is find their individual electronegativities. Oxygen is greater with 3.5. Hydrogen has 2.1. The difference there then, if I subtract that out, is it looks like it'll be 1.4. And then the very last bond, carbon to a sulfur. When I find carbon, I have 2.5, and you'll notice that sulfur is 2.5. Thus, the difference is going to be 0. So when you use the table up above, you can use that scaling system to determine what bond type it should have based on that difference in electronegativity, meaning the pull on those electrons. So since this is greater than 1.7, the first bond would be considered ionic, which should make sense because magnesium is a metal, chlorine is a non-metal. So when we look at it, the formula here would be MgCl2 if we were to have a chemical formula there. So in that example, what we're finding is magnesium would be bonded to chlorine. What we're looking at is this very specific bond. So between this specific magnesium and this specific chlorine, the difference in electronegativity would be 1.8, making it an ionic bond. So then, for example, hydrogen and oxygen can come in many different compounds. One of the options is water, for example. Okay. And so when we're finding the difference in electronegativity, we're finding in this very specific bond between that individual hydrogen and that individual oxygen, how are the electrons being shared? And so with a difference of 1.4, that tells me that this is going to be a polar covalent. So again, I like to include the word covalent because sometimes we forget that we're talking about sharing of electrons and that this is unequal sharing. So carbon to sulfur, we could have carbon tetrasulfide, for example. And so if we were looking at a molecule like that, we're again finding the difference in that specific bond. Not all of the bonds, but just one of these. So then the difference here is 0. So this is a non-polar covalent. So again, to summarize this, if I were to have you find the difference in H2O, you would go through it just like so. You would look up the difference in one hydrogen, you would look up the difference in the one oxygen, and you would get 1.4. Same thing if I had you look up H2O2. You're looking at the specific bond between a single oxygen and a single hydrogen. So the difference in those individual electronegativities will then tell you what type of bond results. So again, you're looking in a single bond, not the overall molecule. That's what the other thing we can do is we can draw a Lewis structure and look at the overall shape of the molecule to then determine what type of polarity we are seeing. So there are 3 rules, and again, we're now looking at the viewpoint of the entire molecule, not a single bond. And so the first example we're going to draw for is ammonia or NH3. What we've done all along is this is through a Lewis structure. So we know nitrogen, there's 1 of them. Hydrogen, there are 3 of them. Nitrogen has 5 valence electrons and hydrogen has 1, so our Lewis structure can contain 8 electrons. When drawing our molecule, nitrogen is going to be the center, and then we can fill in the hydrogens. We know that hydrogen follows the duet rule, so it just needs a chemical bond, so I have 6 electrons. I'm going to add 1 lone pair. So the rule here is it is polar if the central atom has a lone pair. What that means is the electrons are favored more and are going to spend more time towards the nitrogen atom. And so what we did on the previous side is we were looking at this individual bond between a single nitrogen and the single hydrogen. Here, what we're looking at is in the entire molecule. And because there is a lone pair here, nitrogen is favoring the majority of the lone pairs. So the electron distribution is unequal, making it polar. So if you draw a Lewis structure, central atom has a lone pair, it's automatically polar. The next rule, we're going to draw with carbon with 2 fluorines and 2 chlorines. When we go to get our total, we have 1 carbon with 4, we have 2 fluorines each with 7, and we have 2 chlorines each with 7. So we have 14, 28, 32 electrons. Okay. And so what we're going to do is then draw our molecule. We know that carbon is going to be the central atom. And I see that I have 2 chlorines, 2 fluorines. And again, carbon's octet is complete through those 4 bonds. I can then go ahead and spend my remaining electrons. This molecule has enough that no double or triple bonds are required, and nobody has to have an incomplete or expanded octet. So what we're looking at here is our new rule is if it's polar, is when your central atom, carbon, is surrounded by more than one type, because chlorine has a different electronegativity than fluorine. So the type of pull and tug, you can kind of think of it like tug of war here, that the fluorines are going to exhibit a different pull on the electrons than the chlorine. So as soon as your central atom has not the same element all around it, it's automatically polar. So there is only one situation in which your molecule is going to be nonpolar, and CH4 carbon tetrahydride or methane is an example of that. So we know again at this point carbon has 4 valence electrons and we have 4 hydrogens each with 1. Therefore our molecule has 8. Carbon must be the central atom, and we're going to go ahead and surround that out by the 4 hydrogens. So the rule here is it is only nonpolar, and the only way it can be nonpolar is when the central atom has no lone pairs and it's only surrounded by one type. So again, in the game of tug of war, there is no lone pairs on the central atom, and hydrogen has the same electronegativity. So the pole on each of these individual bonds is equal to the rest. That makes it nonpolar, so the electrons will be shared equally amongst everything within the molecule. So the last example then is just a mix looking at Lewis structures. Water, H2O, we have 6 valence electrons from oxygen, and from the 2 from hydrogen, we have 8 available. Silicon, if you look at your periodic table, it has 4, bromine has 7, so there are 32 available electrons there. And then carbon has 6, carbon has 4 valence electrons, oxygen has 6. So with the 2 oxygen, that gives us 12, plus 4, we have 16 electrons. So when it comes to drawing the Lewis structure, oxygen definitely has to be the central atom here, silicon is my central atom here, and carbon my central atom here. I can see based on my formula, in the first one I should attach 2 hydrogen. Again, hydrogen are good once we have added those bonds. And so I have 2 sets or 4 more remaining electrons, which oxygen needs. So 2 lone pairs, and that one is complete. In the next example, I need to complete 4 bonds with 4 bromines. Silicon then gets its complete octet, and the bromines need their complete octet. By adding those 6 lone pairs, that allows me to spend the 32 electrons, and everything is spent, everything is complete. So then in carbon dioxide, we have to be careful here. When we start out with our structure, we're going to bond 2 oxygens, and I'm going to start by completing my octet here. So I've used 8 electrons. So I'm going to go ahead and spend the rest. So here is 10, 12, 14, and 16. So what I'm seeing is that my structure is incomplete. And so what I'm going to then do is have a double bond. So when I go to redraw the structure, this is what I end up with. The big thing to remember is with the double bond is you take from that is complete and share with the one that's incomplete. So when you look at a Lewis structure, you can predict the overall polarity, and that again does not involve electronegativity. You only use electronegativities when you want to look at a specific bond within a molecule. Here we're looking overall. This one has 2 lone pairs on the central atom, so it is automatically polar. In example B, silicon is surrounded by 4 elements of the same type, all of which have the same electronegativity. The central atom does not have a lone pair, thus this is nonpolar. The last molecule here, carbon is our central atom. It has a lone pair on it. That would make it polar. However, if you recall, carbon dioxide has another structure. The other option that you could draw for carbon dioxide involves 2 double bonds. And so in this case, if the bonds are in this format, this would make this one nonpolar. So there's 2 different answers depending on which variety you are looking at with carbon dioxide. If you have any questions, please reach out.